the raw version for just the accelerated gradient descent, which improves the convergence rate of ordinary gradient descent from 1 over k to 1 over k squared, which matches the minimax optimal rate. That's the only assumption that we need to make for reaching the rate is the function must satisfy the smoothness condition, or in other words, the gradient of the function must be Lipschitz with parameter beta. And if we further allow us to assume that the function is alpha strongly convex, then we can get, like, in just vanilla the gradient descent, we can already get linear rate, which is, yeah, let me write it out. Actual gradient descent, accelerated gradient descent. This is O1 over k. And this is like, it is linear rate, but it is linear rate with parameter 1 over kappa to the power of k. Sorry for the kappa k thing. Let me call this t instead. Can you all see the blackboard? Okay. The blackboard is in better condition than previously. Yeah, so this is the rate, the linear rate, and this kappa is a condition number, meaning this kappa equals to beta over alpha. Or if it's like a square problem, suppose we want to solve ax equals to b type of problem, it is equivalent to minimize ax minus b square. If it is a solving linear system using the gradient descent on this problem, then the kappa, this kappa would be the ratio between the maximum eigenvalue of A transpose A divided by the smallest eigenvalue of A transpose A. That's why it is called condition number. So here, with the smoothness and strong convexity, this is essentially like a generalization of the ordinary definition of condition number of a matrix. So this is like the condition number of the function we are minimizing. Okay, so I haven't got to the point. Oh, sorry, I wrote it in the wrong box. The gradient descent has 1 over k to the power of t linear rate. And in accelerated gradient descent with Nesterov's tricks, we are able to add a square root here. Suppose the condition number is very large. Say in most like actual problems, suppose we are doing a ridge regression. And in a high dimension case, then the condition number is essentially the regularization parameter, the regularization weight. That's lambda that this ridge penalty. Then the strong convexity parameter is essentially just this lambda. And we know that for ridge regression to be consistent, we need lambda to be roughly 1 over n. So suppose we have n data point, and the condition number of the parameter will be as large as n, which is the number of sample size. Then this means that taking a square root of the condition number can help us a lot. Say we have 10,000 data points, then the improvement from solving the ordinary gradient descent to solving the accelerated gradient descent would be like 100 times. Okay, so although both these two are linear rate, there is like a notable difference between the two, and it is important that we can reach the theoretical optimal, which is this and that, instead of the typical rate that one might expect from gradient descent. So Suver has already covered all this. It's just a recap, and like he mentioned that. It is always preferable to use an accelerated version of the gradient descent, but we do need to know some parameter in order to use it successfully. For instance, we need to know this smoothness parameter beta in order to set the step size. That is the same as in the gradient descent, but in gradient descent we have like all sorts of other tricks like backtracking line search in order to find something that always converges to the optimal solution. But here, in order for accelerated gradient descent to work, we need to set the step size to be 1 over beta. And also, for the accelerated gradient descent for the strong convexity case to work, we need to have at least an estimation of this condition number. So that also comes up as part of the parameter. So basically, we need like one more parameter to run the accelerated gradient, and we also need to double the storage that we need. For example, we are optimizing over this W, which is a parameter vector. In gradient descent, we can just keep one of these and keep updating that every time we update the solution. In accelerated gradient, we need to take x and y, and then update x, and then use updated x to update y, and then do it another time. So to make an argument more concrete, let me just write out the algorithm for accelerated gradient method. So basically, it is first initialize x1, y1 to be anything. Maybe we can initialize to be 0, and initialize x and y to be the same. Then repeat the following two steps. That is y s plus 1. S is a iteration number. This is just a typical gradient descent step. And note that this gamma s, it is greater than 1. So instead of a linear interpolation between the 2 points, ys and ys plus 1, this is like an overshoot, or sometimes we call this a momentum of the accelerated gradient method. So simply explain, let's suppose but by the way, there's a fixed way of choosing this gamma in the first case, when we only know that the function is gradient Lipschitz, and the parameter gamma needs to be chosen as a function of this kappa if we want to get this rate for the strong convexity case. Let me draw a contour and just make sure everybody is clear with the steps, which may well be the most useful thing from this recitation, because the proof is really not very intuitive. So this is a contour. Suppose we, So, suppose we initialize from here, and this is x1, and this is also y1, right? And if we compute gradient, we will know the gradient point towards this direction. Then we move some small step size 1 over beta, and we get to a different point, and we assign it to be y2. And then the second step means that we want to do it along the direction of y1, y2, along the ray here, to go even further slightly. So we will go just move one more step, and we call this new point to be x2. And in the second step, we will compute the gradient again at this very point, and that will point towards this direction, right? Yeah, actually, I should use a different color. We'll move along the gradient direction, and we'll again get y3. Now, instead of moving along the same direction, the second step, we will do the second step, that is along this direction from this y to here. And we call this point x3. So in general, xs and ys are different points. So it's not like accelerated gradient descent. It's just an increase of the step size. It keeps track of two different points, so it gets more information than as if you use only the first order. You use only the first order gradient information, but you also have this momentum step that deviate you from shooting over too far on this gradient direction, and there's like a curved update from this this x2 point to x3 point, and you repeat until you reach the actual optimal solution. So to make the discussion consistent, I'll also write how are you going to choose this gamma s in the two different cases. For the we can remove this. So let's first define a sequence. Lambda 0 is 0, and define a recursion. Lambda s equals to 1 plus 4 lambda s minus 1 square over 2. Right? So this gives us a sequence of lambdas. And this gamma s would equals to some function of the lambda s over. So this is a step size we need to pick in every iteration. Don't ask me how Nesterov come up with this, or this backend will come up with this step size, but these are the step sizes that work according to the analysis. Yes?
Is there a way to derive these step sizes?
Yeah. We'll see how these step sizes fit into the proof.
They're optimal, like you can't derive.
I wouldn't say that. There are multiple ways of choosing step size that achieves the same rate up to constant. I don't know whether this is optimal up to constant, but it's optimal up to rate. Okay.
So if we know that the function that we are going to optimize is beta gradient Lipschitz,
yeah,
we can use the step 1 as beta. We know that beta.
Yes. Step one. This need to be beta, or at least this need to be smaller than 1 over beta. Yeah. the step size need to be smaller than 1 over beta. So we only need to have like a overestimate for, we need to have an upper bound for this beta parameter, which can be simply obtained if we would like to make a sacrifice by considering the entire domain, the diameter of the entire domain we are optimizing over.
I was thinking about, I know that some people use line search with accelerated
Yeah.
gradient descent. On which part they use line search for finding the coefficient of that beta or the gamma?
There are variations of this method, but here we are using a fixed step size, beta and this gamma. And this gamma is this gamma is like an increasing thing. It starts from 0 and gamma 1 is 1. And we can show that, and we will actually use this, we can show that this lambda is an increasing sequence, which means that the gamma would always be somewhere. Anyway, we will show that this lambda s is always greater than half s by induction. This is something that we will use at the end of the analysis. Yeah, because I might not be able to get to the strong convexity case, I will just put how are we going to choose the step size gamma s here for the strong convexity case. So the update step for the strong convexity is gonna be like, I'll just rewrite the second step. -1. See? So instead of iteration-dependent step size here, we can use the fixed step size here, because now we know that the function is well behaved. Suppose this is a function we are minimizing. Strong convexity basically means at any point we can fit. We can have like a quadratic function. We can have a quadratic function with curvature at least alpha that is always a lower bound of the function we want to minimize. This is f, and this is something that is always smaller than f. Yeah. With the second order term parameter being at least alpha. Okay, so with this good property, we can choose the step size to be fixed, but yet unknown. If we can somehow estimate this, the algorithm will be more useful, and I'm sure there are techniques to do that. Things like property testing, maybe. Okay. Okay, now let's go to proof. So we'll use this definition of the for any convex and beta smooth function. Or sometimes we also call this a definition because it's if and only if condition. If the function is convex and beta smooth, then it satisfies this. The left-hand side is just the first order condition for the convex function. And the right-hand side is something that is given by beta. Yeah. So this is a lemma that you should all be familiar with at the current stage of the course. And is that one of the homework questions? I don't know. Okay, then the theorem we want to prove is a convergence of the algorithm for the beta smooth case. It says that the objective value of the tth iteration minus the optimal objective value needs to be is smaller than 2 times beta. It's 1 minus some constant that depend on the initialization and t square. This is a theorem by Beck. I think it's 2007. And this is what we are going to prove. So like all such proofs, we first need to construct an like inequality that give us the iterations, which is we like just stop me to and ask if you feel any part of the talk is unclear. It is smaller than f. By the way, this is just our first step. The first step in the iteration to descend along the gradient direction by a step size of 1 over beta. This is just a first order condition for convex functions, and it is further smaller than if we apply this lemma to this part of the function, then we will get and this x cancelled out. So this term simply carries down here, and we apply the right-hand side of this lemma. The right-hand side of this lemma, by definition of the beta smoothness, then we can take the difference between these two and take the inner product of the gradient and the difference, and the x canceled out. And again, here the x canceled out. And we have the inequality that we're looking for, which is it's like this is gradient fx, inner product gradient fx, so it becomes just this term, right? And this is also, there's a square here. So this is also the same thing, so we can combine the two terms, and it turns out that the coefficient becomes 1 over 2 beta, minus 1 over 2 beta. And again, this term carries over. Okay, is everything clear? So now we will apply this inequality to x equals to xs and y equals to ys, so that this realizes the first step in every iteration. So if I apply x equals to xs, then it is essentially like I start from xs and do a gradient descent step. So and we will end up with this this is simply that. So apply the inequality down here. Then on the right-hand side, what do we get? We get minus 2 beta and this thing and this thing, they are like the difference. They are the difference between s plus 1 and x. So we can also write it as so here, what I used is the fact that the update step I simply use this step and plug this into the gradient and recovered the distance between the 2 points. On the other hand, I apply the same inequality we obtained here to a different set of points. That is x equals to xs, y equals to x star. And x star is the optimizer. It's the minimizer of the objective function. So that corresponds to what we actually want, what we want to prove. So since we have an inequality, we better try this out. And that's the best explanation I can give about why the heck they come up with this. All the arguments are the same, so I'll simply write the inequality. This equals to oh, sorry, the difference would be xs instead of x star. Yeah. So let's call this inequality 1 and this inequality 2. And then what we will do is to multiply this inequality 1 and then sum it, add it to 2. Then Moreover, let's define the distance between Fys and Fx star, the optimal solution, to be the distance delta s. So let's do the calculation. If we multiply lambda s minus 1 here to the left-hand side and add it to here, what we'll get? We'll get lambda s minus 1 Fy s plus 1. And we have another ys plus 1 here. So adding that in here will simply cancel out this minus 1, right? And we minus f star. And we have a different term. And we have another term that is lambda s minus 1 times the negative of right? So equivalently, we can write this as plus and this as 1 minus lambda s. So as we can see, this is like a linear combination where the two coefficients sum to 1. And then we can decompose this optimal solution into the equivalent two terms and get the difference between ys and the optimal objective function value. S. Yeah. What they actually used is a negative minus 1 here. On the right-hand side, if we do the same calculation here, what we'll end up with is, so basically what we'd have is so this is what you get when you calculate the right-hand side of this. And just trust me that this is correct. The next step is to multiply both sides by again by lambda s. We will have a square here, lambda s here, and square here and lambda s here. So now let's try to work out the relationship between lambda s and lambda bracket lambda s minus 1. I claim that this thing actually equals to lambda s plus s minus 1. So square. So to see this, let's see how lambda is defined. We have lambda s equals to 1 plus square root 1 plus 4 lambda s minus 1 square over 2. And we can do this calculation, and that's right. Can you guys see this? Just taking the squares on both sides. This is minus. Right? And this 1 canceled out. And 4 also cancel out. And we end up with lambda s minus 1 equals to lambda s minus 1 square. Right? That's kind of simple, and what we end up with is that we can rewrite this as lambda s minus 1 square. And for this, we can, because this is a square term, and that's also a square term, and we can put it inside the norm. For this term, that's what we are going to deal with now. So basically what we have is that we have some iterations. We have some recursive inequality, recursive formula for the distance between the current iterate and the next iterate. So this will end up with like a telescoping sum if we sum the equation, and everything nicely cancels out. So we are left to deal with the right-hand side, which is still kind of tricky. We can first add a big bracket here and extract out this beta, so it becomes plus 2. Okay, and 2 lambda s. And this thing, it is like a square plus something that is just note that this term is the same as this s plus 1 minus xs. So it's like we have a square, and we have 2 times a transpose b. B is the other half. And what we need to do, we need to multiply a plus a b square and minus a b square, which will end up with a plus b, right? So the trick is to add a square term of this thing. Let me get a colored chalk. We'll add a square term of this thing, and then subtract a square term of this thing, which would give us, like, the whole thing would give us this is a completed square, and this is a minus the b square. It turns so up to here we still don't know what to do with this thing, even though we can substitute this into the inequality here and then get some different form of the right hand side. But still, this is not where it doesn't look like that this can like cancel out in the telescoping sum, because this is s plus 1, and this is also s. On the right hand side, we have everything nicely as s. So maybe this term is something we need to change in order to construct a telescoping sum. So there's one other thing that we haven't used so far, which is a second update rule. We haven't tried to use a second update rule. So let's start from there and see what is it that we can get out of it. Equals to y s plus 1 plus gamma s. So that's the update rule. And I claim that that by the definition of gamma, I'll just write it here for your reference. Gamma s. So the step size gamma equals to 1 over lambda s over lambda s. So I'll replace this in here and then multiply both sides with lambda s, and we'll get lambda s plus 1. This is further equivalent by just rearranging the terms that and this is precisely what we want. So this means that we can substitute this thing that has like non-harmonious s and s plus 1 and change it into something that has s plus 1 uniformly on all the terms. So that's what we are going to do. We substitute this in. Yeah, for the simplicity of writing, we will like call we'll call this like a different variable. We define us equals to lambda s xs minus. Okay, so we can rewrite that so that the right hand side would be the right hand side of the inequality just now would be it's right hand side. Let me write it on the right hand side. And what we just show is that this is smaller than so the inequality above, the inequality above that after we apply the second iteration, the second step in every iteration can be changed into some nice form where the left-hand side and right-hand side both have like an adjacent iterate. And then we can just simply sum the inequality from s equals to 1 to s equal to t, and by telescoping sum, we will get everything cancel out. So this would be lambda 1 lambda, there isn't any lambda 0, so I have to sorry, this is minus, otherwise it doesn't work. I should reverse the order so that it's easier to see. This is, by using the same telescoping sum, the right-hand side would be I think this term also get cancelled out. Yeah. I think the first term got cancelled out, and all we left with is the last term, and this gives a us an inequality. Delta t is smaller or equals to beta u over 2 lambda and this u1 by definition is simply lambda 1 s1 minus lambda 1 minus 1 ys minus. So lambda 1 is 1. Lambda 1 is 1, so this term goes away. We get the distance between the first initialization and x star. And now it's left to see that this thing is always greater than, is to be always greater than half t. As I claimed in the very beginning, there. This can be seen easily by an inductive argument, by the definition of lambda t, that is there. Let's see, I have lambda s minus 1 equals to lambda s minus 1 square. Suppose for lambda s minus 1, this is satisfied, then we will have and this is smaller than lambda s square. So these two terms give us exactly the inductive argument that this hold. So by induction, this is smaller than beta. It's 1 minus t square. And the 4 2 is cancelled out with this, and you're left with 2. And this is given in the theorem over there. So by this line of very tedious algebra, we managed to get the 1 over t square rate for accelerated gradient descent. So looking back at it, it's again not very illuminating. It's like starting from the first order condition for the convex function, and then apply the beta smoothness condition to get some iterations. And after that, we establish two relationships, one between xs and ys, which is the 2 points x and y in every iteration s. And the second, we bound the difference between any xs and the optimal solution x star in terms of the objective function value by applying the same inequality. And we did this like magical trick. We did this magical trick to construct to somehow construct and iterate, that is for the difference of the objective value and the optimal objective value. And on the right hand side, we apply the second step in every iteration to get to get something where we don't know what to do about on the right hand side. So with that, we plug in all the plugging out the algebra, and it gives us a telescoping sum on both the left-hand side and right-hand side of the inequality, and that turns out to give us the rate. Yeah, I can briefly explain how do one like prove the strong convexity, a strongly convex version of the rate. They basically construct like a surrogate function. Again, let's see. This is a strongly convex function that we want to minimize, and we know that by the strong convex condition, we can always, at any point, we can always find and underestimate by a quadratic function. And at the same time, they construct some function called phi, a sequence of function phi sx, which approximate x fx when s goes to infinity, when s go to become large, and that function actually look like some shifted version of the same quadratic function here, which is centered around this. And the second step in the accelerated gradient algorithm is an interpolation between these two functions, and find the and then like just some interpolation between this and that by some predefined ratio, which is something related to the condition number. So afterwards, the proof will show that for any s, fx s will always be smaller than the minimum of x for this phi x. And with this and some iterates they constructed, they will be able to show the fancy linear convergence rate for the strong convex functions. So I don't have time to talk about that, but all these are in Nesferov's 2004 book.
Okay, so I don't really understand intuitively how that uses strong convexity.
I don't either. That's how they prove the stuff by constructing a sequence of function that converges at its minimum to fx.
So how does that sequence depend on the strong convexity parameter?
It depends. Well, it depends a lot.
Okay.
So this phi sx is simple to write. It is also a recursive definition. So they use induction a lot. So x1 is the initial point, and phi 1x equals to this plus a quadratic term. So this is basically a constant, and so as you can see, this function is exactly, say this is x1. It's exactly there when we take x equals to x1, and it is always greater than that as a quadratic function. And the recursive definition of phi s plus 1x.
So basically, alpha dictates how steep those parameters.
Here's where the condition number comes in. And plus some really complicated form that is that comes from the strong convexity stuff. Plus alpha square. Yeah, that's their complicated definition for the phi. And one can show that this sequence of function converges to something that has this property, and also another property is that this function is always basically by constructing this function, they are able to get a factor that looks like 1 over square root kappa to the power of t. And by combining this property and the other property that contains this factor, they are able to show the linear rate of convergence with that factor. So it's really not very clear to me how they come up with the solution. Like Suvert said, it's more or less reverse engineering. And it's not very illuminating, but it contains many of the important steps of typical gradient descent proofs. So these are the ways how strong convexity and smoothness are used. And when you have like iterates, just try your best to form either a telescoping sum or some complicated inductive proof technique to somehow make it work. Yeah. Before do any of this, test your algorithm empirically, see whether it really works or not. If it does work empirically, you can think of a way to try to prove it. Otherwise, don't bother. Okay. Yeah.
Thanks.
Sorry that